Today I have the great pleasure to welcome Carlos Eduardo Valero. He is originally from Venezuela, has 2 master's degrees, one in bioengineering, the other one in control. And he's currently a PhD student with the Slovak University of Technology. There he's working in the research group of ROPO. And currently he's on a research stay in Germany at the Technical University of Munich, and we're jointly working together with Matthias Althoff there. And yes, from that perspective, I will hand over the microphone to Carlos, and we're looking forward to your presentation on ROPO Extreme. This will be some method on set membership state estimation.
Thank you, Andrea. Okay, hi everyone, I'm Carlos, as Andrea said. Today, I'm going to try to introduce you this new method in ROPO in set membership state estimation. The main idea is to take information from the past and use it in a current state. The idea is to reduce always the reachable set as much as we can. Okay, we are already with the introduction. So as a motivation, we have a dynamical system. This dynamic system could be a non-linear system. We're going to see how. Usually we have some inaccuracies in some sensor. We usually see that V to K and omega to K are uncertainties or non-linearities. And we're going to see that our states in general are inside some convex bounds. For example, the states are in a convex set, something like this. The uncertainties and non-linearities usually belong to some non-convex sets. And we have some uncertainties on we have some noise on the measurements. So that is going to lead to another set. All these sets have a different distribution. So it's going to put a little more complex the problem. So in this case, it's just a compilation on some distribution. So what do we want? We want to achieve the value xk in all the time. But I have bad news. There is no way to get this value. Why? Because we have some uncertainties that are to obey to some random processes, and this is not easy to get it. And there is no way to get it because it's going to change randomly each time. In the same way, we have some inaccuracy in the sensor. So how to design an observer that guarantees the state of the system? This is another problem. It's going to be a little more easier. It's going to be easier. So there are many options. We have in the robust estimation problem, we have extended Kalman filter, Lumberger observer, moving horizon estimation, and what we are going to talk is set membership state estimation. In this sense, we know that this methodology only needs measurement and uncertainty bounds. We can use parallelotopes. One of the work here of Vicino is the most known. Some topes, there are a lot of research that work on this area. We have Alamo, Althoff, Combastel. There are many. Yes, Fogel for ellipsoids. He has been developed a lot of this in theory, and he is without doubt the father of this area. And polytopes. We don't have too many people working on polytopes in Hasse space. It's important to recall that all these ones are polytopes. So all set-based estimation techniques require a trade-off between accuracy and low complexity. This low complexity basically leads to computational cost. So it's something that we need to handle it always. So what is set membership state estimation? We have a set where our system is. We have some X. And usually we need to move it according to the dynamic. This is applying some transformation, in this case a linear transformation, but actually it's an affine transformation if we include the control input. Yes, and sorry. Okay. After this point, we have some uncertainties on some non-linearities that we know that are bounded in some sets, in this case, this one. And we're going to apply a Minkowski sum on this set. We're going to get now a new set. Many researchers call this set a reachable set. And to this space, they call it a propagation step. This is actually more my definition, more the definition that I like, sorry. And on the other hand, we have in a parallel way, the construction of the output set. This construction starts with the measurement output and one bounds where are the outputs. I mean, the noise bound. So we are able to build an output set that is going to lead to the intersection. And this intersection is actually the feasible set that we want to get. And to this step, we call it update step or intersection step, depending on which author you see. And something important to say, something important is that we never can get the exact intersection. Why? Because it's high computation, imply a high computational cost. Therefore, we usually take some over approximations. So what we want to do is create a new output set using some information. We are going to see how we're going to take it. That is going to lead a smaller intersection. That is going to lead a smaller over approximation of our reachable set. That is the main core of ROPO E. So first of all, we need to understand we need to establish some fundamentals in mathematics in convex sets. We're going to work with parallelotopes that actually are sonotopes over one. We have the generator matrix, that is T, and we have the center of the parallelotope. As you can see, this is a polytope that has two half spaces parallel. So, and we can see a set of half space representation in this way. Why parallelotope? It's a sonotope, as I said before. So because imply simple tasks. The linear transformation is quite simple. If we have a matrix, a non-singular matrix S, and we have a vector Q, we know that the linear transformation is going to be given by this. So it's just going to be a transform the way and shift a little the set that we got with the vector. We can apply Minkowski sum in a really easy way. But this is not a parallelotope, this is a sonotope. Therefore, if we want to work with parallelotope, we always need to reduce in this step. And the intersection in general is not a parallelotope. However, we can find, using some algebraic relation, we can find an over approximation of one parallelotope that includes this intersection. This is our over approximation proposition. We can see it later. So now let's go for strips. A strip is basically two half spaces. Two half spaces that are written on this way. H plus and H minus define the supporting hyperplane of the strips. We can see that this dot line is going to be P transpose X equals C, because it's exactly in the middle. And this is basically the definition of strip. So something we need to understand is that we need to move the strip according to the dynamic of the system. So when we try to do this, we couldn't find a way to do it. So in the literature, we didn't find it. So we developed it. We noticed that this is the strip propagation, that if we wanna move a strip accordingly to some dynamics, where A is a non-singular matrix and PU is a vector, we have to do it this way. What is the proof? Okay, let's start with this proof first. We have some dynamics. This is the current dynamic that we have. So we can express xk in terms of xk plus 1. So it's basically just find x. Now we can express the strip of k in terms of xk plus 1. That is going to lead in a strip propagation, right? So we just change replace x for xk plus 1 for this expression, sorry, and we're going to get this expression. After reordering, we got this. So clearly, based on the definition here, we can see that this area is going to be P transpose, that is this, and this one is going to be the chief value of the strip. So it's proof that this is a strip. So that this is a strip propagation. In the PC conference, we have a different proof, but it's still the same. It's another way to reach the same result. So let's focus now on what is ROPO, or what are we going to do to set member state estimation with parallelotope. First, we need to build an output set using some strips in this case. After that, we need to propagate our parallelotopes into a, let's say, a predicted parallelotope. Yes, this is the reachable set. And what we want to do is to find a parallelotope that includes this intersection. There are many methods, but one of the most famous is, without doubt, the recursive optimal parallelotopic outbounding. It's better called ROPO. And it's an algorithm that developed the method in 3 steps. The first one, he reduced the strip. After that, he reduced the parallelotope. And after, he tried to find, actually the minimum volume of the parallelotope using this strip, or this strip. So if you want to go for more details about this method, you can go for Vicino and Zappa in 1996. Okay, what is ROPO exactly? And until this point, we're going to take a predicted parallelotope, and we have a current measurement. So we're going to get something like this. If we start here, we notice that we can apply ROPO, and we're going to get the ROPO algorithm. What is the difference? What if we can add a new strip? And I'm going to call it maximal error measurement. So if we add a new strip, hopefully we're going to get something smaller. And what if we add another one? So we're going to reduce even more the intersection. So in this point, after we apply this, we use ROPO. I mean, we found the parallelotope with a minimum volume that encloses this area. But now this area is evidently smaller than the first one. So the first time that we get this one, it was on dicots. The inspiration of this, it was given by Chris in 1998. He proposed some similar method when he takes on deepest strip on the system. We are going to get something related, but it's still completely different, right? So the biggest problem here is how to determine the best index criteria to find the minimum and maximum strip. Sorry, in this case, it's quite simple. If we draw a line, a horizontal line here, we can see that the red line is going to appear first than the blue one. And if we do it in a vertical line, it's going to be the same. So without doubt, the red one is a minimal and the blue one is maximal measurement. It's easy to define. However, this is not always the case. So we have a parallelotope, and maybe we have a strip. So the first idea that we have is to draw or to find the distance between the center of the parallelotope with the center of the strip. And this center is the hyperplane that led here. I mean PTX equals C. For this purpose, we have some problems. This is the distance between a point, the center, to a plane, and it's given by this. But we have some problem. What if we have another strip, and this strip have the same distance, right? So even when they are completely different, we should actually select both, because one could be minimum and maximum. So maybe you can see on this distance and this distance, I mean, we draw a horizontal line and try to compare the center with the strips, but we don't know how to get that distance. That distance looks like, because it's longer than norm 2, maybe it's a norm 1 distance, but we are not completely sure. Another way should be the projection between a point into a plane. What is this? We're going to get this point. We're going to get, from this point, we're going to project it into the plane. We're going to get this point, probably. And after that, we are going to use the knowledge that we have about the output, and we're going to make a subtraction. After we let with some reduction, with a simple reduction, we can get some distance that is going to be like this, or some index that is going to be like this. This index have one particularity, this minus, one of them. This index could be positive or negative. This is something good. And is extremely related with the outputs related with that strip. That is going to be more efficient than this one. So this is one of the things that we think that could lead a better result. But actually, why do we have to compare with the center of the parallelotope? And this parallelotope, what does it mean, this parallelotope? Is this the predicted parallelotope? Or is this the reduced parallelotope that we already have it? And why the center? Why not a vertex? And which vertex? So these kind of questions that we actually don't know with exactitude, with precision. We take the center of the predicted parallelotope, actually the reduced parallelotope, because it's close, I mean, expose the minimum distance to all the faces of the parallelotope. So within is the more robust or more discrete value to compare. But we are not completely sure. And why do we have to compare the strips with the parallelotope? Why don't we compare it with the measurement output? So we don't know it exactly. Right now we're working on a new projection, and we think that it's going to lead a better results that is using this index performance. But actually in this point, any suggestion is going to be always welcome. So what is ROPO? ROPO basically keep a strip with external measurements. In the previous one, we discussed how to get these external measurements. We propagate the parallelotope and the external measurement strip through the linear dynamics. This is something good that we get, because at the beginning, we were propagating parallelotope, inverting the parallelotope, and getting out the strips. Now we are doing this only in one step. So we can work with high dimension systems. Is dimension or high? We perform estimation, taking new measurement information and external measurement. We update external measurement based on the prediction error, To go a little more deeper, you can always check this in paper. This was on PC 2019. Okay, let's see some simulation that we have. If we compare a double integrator, in this case, we are not going to use uncertainties. We're going to use just a linear system without uncertainties, only some unbounded noise. Sorry, bounded noise. We are going to add some constraints on the input and the state. We have some initial conditions. We have an output with some bounds. Okay, you can find this configuration in dicodes. And this is actually the result that we got. If we compare ROPO with ROPO-E, we can see clearly a difference in the bounds of the state. And this leads to a difference, once more, resolved estimation. This estimation is once more the center of the parallelogram, of the resulting parallelogram in that step. When we check the performance, we see that in all the realization that we made, always ROPO-E was the winner, and we actually reduce the accumulative performance. For this purpose, we use an MPC and we take the vertices of the system. So the method works. So what conclusion we can get? So the most important is that it's possible to enhance the set membership state estimation, taking into account past measurements of the system. This is ROPO with external measurement. I mean ROPO-E. The propagation of one street according to the dynamic of the plan. This actually could be really simple once that we get it, but at the beginning it was really hard to get it. And the static concepts apply to other bounds error estimation. Sonotopic Kalman filters, sonotopes, or high order, and any other. Because if we think we are just taking information from the past, we propagate this information based on some index criteria that define the maximum and minimum, and we apply like we have a multiple output system. So this is actually everything. Any question, please, are welcome. Any doubt, any idea, please, you can send me an email. We can discuss it here. Thank you, everyone.
Okay, many thanks, Carlos, for your presentation.
Thank you.
I think it's time to give you a hand of applause for this talk. And now I think your presentation is open for discussion. Does anyone want to start?
Yes, please.
Yes, Nassim?
Yes, Nassim speaking. Thank you, Andrea, for organizing Andrea and Tarek via extreme measurement. What is the complexity of finding the extreme measurement in a
is corresponding to the state of the system, and the other two to correspond to the strips that contain the external measurements. When we propagate this, we get the inverse, and we get the strip from this measurement. When we start to use the another article, we notice that the inverse have or led a lot of problems, because from this problem of the accuracy and all this stuff. So to find the strip, it wasn't a problem, but to propagate the strip, it was the biggest problem. And for that reason, we start to use the strip propagation. We need to change it. We have to change it to that. And to be specific about how to define or how expensive it is to define the extremal measurement, it was here. In the last article that we have, we compare it using the distance between the point of the strip to a plane. And this is given by this formula. We actually compare this distance with any other, and we define the biggest one is going to be the major one, and another one is going to be the minimum. So I don't know if this answers you the question.
So you need to propagate all the past data to compare.
Not all, only two, because I'm going to start actually with.
Okay.
Yes.
You do it on the fly. We compare the current maximum with the current data.
Exactly.
Okay. So okay.
Okay, maybe let me add a question here to that point that Massimo already discussed with you. I think one of your limitations is this strip prediction approach that does not allow you to take into account, for example, system matrices that are singular. For example, if you have a closed loop control system in which you have some deadbeat behavior. Do you have any idea how to deal with such a phenomenon?
Yes and no. Why yes? Which part is yes and which part is no? Right now we're working with discrete systems. In discrete systems, the only way that you got some zeros, some singular matrix is that you have some zeros. That means that the poles are infinite. So this is never going to come in a discrete system. We always can or rediscretize or redefine the system for discrete system. I mean,
okay, that means you always take into account a discretized open loop dynamics and not a discretized closed loop dynamic system.
Yes.
Because if you take into account the closed loop one, then you can have the eigenvalue at 0.
Yes.
Okay.
Exactly.
I have two small questions. The first one is how to proceed if the matrix A is not invertible. And the second one, do you need some assumptions such as observability or detectability?
Okay. Regarding the question of the invertibility of the matrix A, yes, we don't know how to do it. Yes, we need to redefine the system and to find a minimum system that is going to be depicted, but only the state. I mean, there are some relations, some linear relations between some rows or some. So the idea is to reduce the system. And to work with a reduced system is going to be actually simpler after we got this system. And sorry, what was the second question? About the detectability and observability?
Yes.
I mean, for the propagation step, we don't need it because we only need the dynamic of the system and we're going to propagate it. However, ROPO lies on the intersection step. And for the intersection step, we need that our system is observable. I mean, at least detectable. Yes, so we're going to get only information about some states, but we need it. Yes, so our system has to be at least detectable. On the contrary, we cannot reduce it. We cannot use the reduction.
I think that you don't need that the matrix is invertible. For example, if the system is observable, then you can introduce again L such that the matrix A minus LC is invertible. And it is always the case if the system is observable. You can
Excuse me?
These results, I think.
May I ask a question?
Yeah, of course.
Yes.
I'm a professor of Tongji University, and I noticed that in your computation, you noticed the inverse of the matrix A, and this means that your method is only applied on the systems with which the matrix A has to be inverted. Inverse, do you understand me?
Yeah, yes.
The matrix you come in your computation, you use the inverse of matrix A. So your method is only applied to the system which A is inverse.
Yes.
Doesn't it?
Yes. Yes. It's true.
So is it a stronger restriction of the method? Restriction.
Sorry, no, I don't get it. This
Restriction of the method.
okay,
yeah, that's
yes.
right.
Yes. This is a restriction. There is a wide world of systems that are full dimensional. In once more, in some discrete systems, it's really hard to get some A not invertible, because that leads that you have some poles in the zero, and this means in the continuous system that they lie on infinite. So something that is a great advance of discretize the continuous systems is that we can always get an A invertible, right? If we don't get it, we just change the sample time to another one. It's another story if we start with a system that is discrete for the nature, right? But if we discretize a continuous systems, we can always get an invertible matrix A.
Okay,
So,
I think, yes, please continue.
So the A has to be invertible.
Yes, it has to be. Yes,
Okay,
at least to
okay.
propagate the strips.
Okay, thank you.
Okay, I think we have a question from the chat. Vincent, do you want to ask your question yourself?
Yeah, sure. Hello.
Yep.
Thank you for the presentation, and thank you for organizing this seminar. So my question relates to, so I'm mostly doing robotics, and in robotics, the state equation of the systems are mostly nonlinear. So they are state dependent. So for example, your mass matrix is a function of the state of the system. So when you're in the prediction phase, you can only predict for a small amount of time. And I was wondering how you would deal, maybe it's a very naive question, but I was wondering how you would deal with such a kind of system at the prediction phase, where you can, I mean, the horizon of prediction that you can have is limited because of the fact that your system is nonlinear and is state dependent. Does the question make sense?
Yes, I have a lot to say. I mean, your question, correct me if it's not, is about how can I propagate a nonlinear, based on a nonlinear dynamics, a strip, for example. Is it?
Yeah. That's typically. I would like to have a hint or an idea of how you would do that efficiently and without compromising too much precision. Something like
okay, that is really good. You please, you can send me an email. You have it here, and we can always try to figure out together how to get it. Is carlos.valero@estuva.sk. We in IFA World Congress, we developed some method for polytopes, and we try to find some bounds on the nonlinearities and use this bound to propagate the system. But there are always many options, and maybe yours is the best. Oh,
I don't have any option. It was an open question. I don't have any option on my side, but
sorry. Okay, so we can establish some bounds on the nonlinearities based on the value of the state in that point, and use this bound to propagate the system. We haven't used this principle to propagate the streets, but it should be leading over there. So we're going to try. And that is a great idea.
Hey, maybe let me reformulate a little bit this question. Is your idea something like turning the state dependencies in the system matrix and also in the input matrix B into, let's say, some kind of polytopic uncertainty model where you have time varying parameters, and that you try to propagate a system model with time varying parameters from one step to the next?
Okay, not until the moment, but I am really open to that. We are really open to that. So please write me for any idea and we can discuss it. It's going to be nice for them.
Okay. Thank you very much for the answer, and I will probably write to you. Thanks.
Okay, we have a further question here. Alex has raised his hand.
Hello. Well, my name is Alex. I have a question concerning the application you have shown in your example and also presented in the ICOPS paper. If you have applied your approach here for propagating the uncertainty in model predictive control, I wonder if you have made a comparison with the existing techniques like tube MPC or even the one you have cited about Alamos for the zonotopes, and if the comparison is, how can I say, stronger for you. I mean, if you have any guarantees on robust constraint satisfaction or anything like that.
Okay, we haven't compared with tube MPC. Actually, it's one of the future work. I would like to do it. We compare only with against ROPO itself. ROPO has been compared with ellipsoids in the same way, not with polytope in half a space, but we are really eager to do it. Not until the moment. We haven't compared it with all the possible dynamics, but it's one of the work that we have to do. So.
Okay, but my question also concerns about the complexity of solving online the optimization problem. Does it get harder to solve the problem as using another techniques or not?
Yes, but okay. ROPO in particular have a good quality, is that he doesn't need any optimization problem to guarantee optimal volume into the system. That's something really good. And of course, because ROPO is based on ROPO, we have the same advantage. And when we are using moving horizon or tube MPC, we need to make many optimal problems. So, and we need to develop many, many linear programs. And maybe this is not so high, but we don't have it. So if we compare only on the cost, on the possible cost, I would say that we have a lower cost in terms of the complexity. But I cannot guarantee. I mean, we haven't compared it. We haven't checked all the parameters. So I cannot say that this is the best always. So, but I can say that at least we have these slides. We know that we don't use any optimization program to get this one. We know that moving horizon estimation, for example, take a lot of optimal problem to guarantee the same than us. So I think that we are going to get the same results. I mean, ROPO is going to be less complex than other approaches.
Okay, thank you very much.
You're welcome.
Hi,
Yep.
I have two small questions. First, could you please turn to page 8?
Yes.
In your method, in the step 3, yeah.
Yes.
How to choose the minimum volume paratope? I mean, is it very difficult to obtain the minimum volume or not? What about the complexity?
Okay.
This is the first question. Please answer this question first. Thank you.
How can I choose? Yes, sure. How can I choose the minimum volume of this parallelotope? Okay. Of course, in this case, this is an example, right? I mean, I didn't perform anything here, but Vicino established something really good. And he noticed that all parallelotopes are always defined by the intersection of n strips. So it means that this parallelotope, the blue one, is built with two strips, once here and another one here. So what do we have here is the intersection of 3 strips. We have these two plus these two. So what Vicino found, it was that he only needs to compare the volume of all these combinations. See, he needs to find the volume of this parallelotope of these two. He needs to find the intersection of this and this, for example, with this one. There is another polytope, and the third one should be this and this. So it should be this parallel, something like this. So actually we have three parallelotopes. We have n+1 parallelotopes, and we compare the volumes. The best way to do it is, okay, let me find first, sorry. Let me show you the specific example, because we can compare it only changing the column and comparing with one parallelotope, right? So this is just
okay. So we have to compute the volume of polytopes, right?
yes, for parallelotopes.
Okay. Okay. And if there are many measurements, so we have many strips. How about this situation?
Okay, there are two. Yes. There are two different ways to do it.
Okay, please.
Yes, we have two ways. Or the sequential approach, where we are going to get one strip, we found a parallelotope, and we use another strip, and we intersect again, and we use it once more. This is the sequential approach, or the block approach.
Okay,
right? The block approach implies a linear problem, but it's a linear problem. So it's not so high.
Okay, I see. Thank you. And my second question is that did you consider the stability of your estimation methods?
Sorry?
Did you consider the stability of your method?
Okay, not directly. I mean, when we are taking the MPC, when we are estimating into the control, for guarantee this, we need to take always the internal parallelotope. So what we do is we run the MPC, and if we got infeasibility, we change the parallelotope to the internal one, because the internal one has the same properties than the previous iteration. I mean, sorry, you can see this one, right? We always take, sorry. If you think, in the first time that I ran the MPC, when the MPC works, he used this parallelotope. So he have to move the dynamic of this parallelotope many times to achieve. So after we ran another, we got that our parallelotope, it was this one. However, we get some infeasibility here. So it's a problem of stability, it's a problem of feasibility problem in the MPC. So what do? We change to this one, to the minimum one. So we are not going to choose always the minimum volume, but we are going to choose always the feasible, parallelotope. So this leads to stability and feasibility in the optimal problem.
Okay.
And sorry, Shenhuan, this is the way that I told you to compare. Sorry. This one, the equation 35. So we only need to compare the volume of the first, and after that we divide between each column. This is going to lead a easier way to compare all the volumes. So we only need to find the computation of one volume, that is the first one. He called it P0. You will see how it is. And after that, we just change the column, and we're going to find it. It's better. I mean, to compute. It's better than compute all the three different volumes and see what is the minimum.
Okay. Okay. Thank you.
You're welcome.
So do we have any further questions?
Yes, please.
Yes.
Okay, so maybe a more general question. The main feature of your approach is to propagate the measurement strips. So my question is, can you may apply your approach to set estimation with zonotopes or ellipsoids and so on. So do you think it may be a good idea?
Yes, I think it's a great idea because the main of the extreme measurement is to take information from the past, right? And this information from the past, select it in a heuristic way and use it into the current measurement. So we always can use this kind of approach to different strategies. However, we always have to let with the propagation in one's, if we choose a set that is not well defined or how to define this propagation. And we need to find the problem with the intersection or the reduce. I mean, a parallelotope is a sonotope, but it's not, it's other one. So have a little more special.
I mean, if I can reformulate, the current state-of-the-art methods, they do propagation and then intersection. Yes. So you have several recipes for computing the intersection of a strip with a ellipsoid, yes, zonotope. You can compute the intersection between zonotopes and so on. And the feature of your approach is that you propagate what you have defined as extremes strips. Yes. So I was thinking that maybe this is a general idea. You could apply it to any type of estimation technique, provided that you have a non-singular dynamics and yes, and you can, and the linear
yes, exactly, yes. This,
and
that is
yeah, and as well you may provide some answers to the questions regarding the extension to non-linear systems, because you can use zonotopes which are more convenient for dealing with non-linearities better than the parallelotope, who might introduce some spurious over-approximation. So, okay,
yes,
thanks.
Thank you.
You're welcome.
Yes, maybe let me add something to this question of Nassim. I think what would even also be possible is to perform multi-step predictions of the strips. That you do not only predict from one step to the next, but let's say predict for 5 steps or 10 steps in order to reduce some pessimism.
Okay, we never think actually on that.
Yes, because it's just an iterated form of the set of discrete time state equations.
Yes.
Yes, a projection of the measurements onto the state space.
Yes.
Yeah.
Maybe a suggestion for some outlook or for some future comparison. Did you try to compare your approach with some interval observer techniques that account for specific system structures, for example, like Metzler matrices? Because when we go back to the slide number 12, your system matrix in the example has a very special structure.
A
12, the matrix A on slide 12.
Yes.
Yeah. All your off-diagonal elements are strictly greater than or strictly non-negative.
Yes.
And that allows you to derive easily some bounding systems. And maybe this could also help, for example, Alex's questions, where he said, okay, propagating parallelotopes may be quite costly if you take into account predictive control approaches. There you could combine some bound propagation, conservative bound propagation from the classical interval observer community.
Yes, I mean, the coefficients here are convenient, of course. But it's not really, it's not a bound, it's not, our methodology doesn't depend exactly of this coefficient, because one of the ROPO advantage is, or one of the parallel advantage is that this column could be positive or negative.
Yes.
And it's going to be the same parallelotope. So if we got a negative, we put it positive and we run our algorithm. And after that, we got the value. So for that reason,
that's true. But in some specific application scenario, I think those approaches could mutually benefit from each other.
Okay, yes. Yeah, I mean, I'm not sure, yes. That's a good idea.
Okay, anyone else who wants to comment or discuss?
Maybe a small comment or suggestion. Yeah, you could try also to cast your work in the constraint propagation framework, and the work of Luc Jolin and his colleagues, where they did some constraint propagation on nonlinear state estimation, where they mainly do prediction correction, but they do it forward, backward, and they also propagate the measurement. They propagate the output feasible set forward and backward in time using ideas similar to the one you are investigating, and they do it in nonlinear settings. So maybe you can have a look to their work, and it may give you some ideas to go towards the suggested.
Sorry. Who is this person?
The person? Okay, is
which
Jolin.
are the author?
I can send on the chat maybe
please
the name. Yeah, the author is the work is Jolin. Yeah, the name is Jolin, and there are some. They are in a nonlinear settings and using interval computation, but more than that. But maybe there are some ideas you can benefit from,
definitely.
In particular to exploit the suggestion from Andreas regarding multiple time step ahead and so on.
Yeah, if I may add to that, exactly what Nassim, what you are saying is where this somehow leads to. That's the also connection to the nonlinear systems, because these guys develop some techniques to deal with the nonlinearities, exactly as you say. And generally, if you want to deal with nonlinearities, you would need some kind of nonlinearity bounders, so some kind of outer convexification techniques for the general nonlinear systems, which is currently still a very open topic. Some people have ideas, very good ideas on how to do this on some small scale system and some specific nonlinearities, but yeah, it's somehow similar to the global optimization and these techniques where you are trying to somehow capture with the convex sets the non-convex ones.
Thank you, Radoslav.
Maybe a final question from my side concerning possible applications. Did you already try this method for some real-life physical application scenario, for example, to process real-life measured data?
Okay, no. Right now I'm working on some model for road common for some cars with Matthias. I'm applying this compared with Sonoto, but not exactly with a real plant.
Okay.
I mean, not ever. So it should be hopefully.
Because I just thought about the aim, for example, of applying your techniques to some process control problems, because Rado in former times also worked on such problems. Yeah. Okay. Does anyone else want to comment or ask questions? Yes, Rado unmuted himself.
Yeah, I mean, we have a nice distillation column standing.
Yep, this is something what I was thinking about.
Yes, and yeah, we are hoping to get there. So that it's a small distillation column. It wouldn't require that many states. Yeah, that might be very interesting one. Yeah.
Okay, if we do not have any further questions, I think it's time to wish you a nice weekend or depending on, yes, the place we are situated, nice evening, nice afternoon, even nice morning. And yes, in 2 weeks, we will continue with our next seminar. The next speaker will be Zhepeng Zhu from the Tongji University in Shanghai, and he'll talk about interval observer-based anti-disturbance control strategy. Again, many thanks, Carlos, for your presentation. I hope that Zoom will allow me to automatically convert your talk into an MP4 video, and this will then be uploaded on YouTube. Okay, see you all again in 2 weeks.
See you. Thanks.
Bye-bye.